So in this video I want to look at optimization. That's yet another application of derivatives. So I have pasted in here a problem from Larson and Edwards Calculus 8th edition book. The problem says a farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 18,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing if no fencing is needed along the river? And optimization problems generally always come as a word problem when you're trying to optimize, whether it be maximizing or minimizing something to gain greatest efficiency. So first thing I always recommend is draw a picture to help you get your mind around things. So if we draw this, we have a river. So here's our river running along. We have a pasture off of that that's rectangular. So our pasture looks like that, and the area is 18,000 or 180,000. Now we want to find what dimensions would require the least fencing. So we're talking about trying to make the perimeter as small as possible and still maintain the area of 180,000. So if we make the sides distance x and the long width distance y, the perimeter will be 2x plus y, because we don't need a second y. The river is the border on that side, and our perimeter is going to equal, or the perimeter is what we're going to be solving for, so that's just equal to p. But we can also write the equation for area of a rectangle's length times width, and we know we want that to be 180,000. So from that, I hope you're beginning to see at least where this is going. If we take our second equation for area and isolate for y, we can plug it into the first equation and have the perimeter in terms of x. So if we just take xy equals 180,000, divide by x, we get y equals 180,000 over x. So then we can plug that into our perimeter equation. Perimeter is equal to 2x plus y, which is 180,000, over x. So now we have an equation that represents the perimeter in terms of just the side x. Now to optimize this, we need to find what makes the perimeter the smallest. Well, if we think about it, this is really a graph we're working with. We want to find the minimum on the graph. And how do we find a minimum? With a derivative. So what we're going to do is take the derivative and find the extrema, and that will tell us what x value will give us the minimum perimeter. So the derivative, and I'll just call it p prime, will be 2 plus the derivative of 180,000 over x. Well, we'll take the x to the numerator, use the power rule. It will come out to be negative 180,000 over x squared. So now to optimize that, we set it equal to 0. So 2 minus 180,000 over x squared equals 0. So to solve for x, first I'll go ahead and add the 180,000 over x squared. Get 2 is equal to 180,000 over x squared. If I multiply by x squared, I get 2x squared is equal to 180,000. Then divide by 2. X squared is equal to 90,000. When I take the square root, x is equal to plus or minus the square root of 90,000, which we can simplify to being plus or minus 300. So at x equals plus or minus 300, we have extremas on the graph of our perimeter function. So then we have to see, is it a maximum or a minimum? And we can use a first derivative test, see if it's increasing or decreasing, and tell if it's a maximum or a minimum. But in this case, it's pretty obvious that negative 300 can't be an answer because we're talking about distances. So positive 300 is our only extrema to work with. and that will be our minimum. So at x equals 300, we have a minimum. If that's the case, how much fencing will we need? Well, we're going to need x plus y, right? That's our perimeter. Well, we said x is 300 and y is 180,000 over x, which is 300. And we simplify that to being 600. So we'll need a total of 1,200 meters. We'll need 300 meters on our 2x directions and 600 in the y direction. So we can say that the total perimeter will equal 300 times 2 plus 600 meters, which is 1,200 meters.